Hello, I'm Gabrielle Taylor. I'm going to be doing homework for Part C. So the first question is we're going to use the final value theorem to show the PI control of a second order process with a measure transfer function of 1. It will always reach its desired set point. Okay. So the first thing we want to do is do our block diagram. So we have some set point here as y set point, so some set point. We have our Fn here, right? And so it goes in, and we're going to have our, we have arrows. I'm going to just do this. So we have our GC, and then we have our GP, which is our actual process, and then we have some output of y, right? And then it has a closed loop system here, and this is where it's going to measure that set point, right? So GM, so that's where it's going to measure our set point. So the first thing that we want to do is we're going to do our GC1, and the top is going to be our forward direction, so it's going to be our GC times our GP, and then the bottom one is going to be our closed loop system, so it's going to be 1 plus GC, GP, GM. Next is our GC, right? So we want to do our GC, which is our KC, times 1 plus S times tau I over S tau I. Then we have our GP, which is equal to our K over our S tau plus 1, and then remember when we said it was second order, so this is going to be the second order, and then we have our GM, which is equal to 1. So then we want to plug this all back into our GC1. So we'll have is KC 1 plus S tau I over S tau I times our K over S tau plus 1 squared over 1 plus our GC, which is KC 1 plus S tau I over S tau I times our GP, which is K over S tau 1 plus squared, right? So after this, we're going to use our final value theorem, so FTR, and we're going to take the limit as S approaches 0, and so we're going to multiply this by S, and then we have our GC1, and we're going to multiply this by A over S, right, because this is this is going to divert from steady state, and when we divert from steady state, we need to use our Laplace transform theorem, so we have our A over S, so, with our set point. So, we can see that these S's cancel out, right? Oh, and this equals our Y to infinity here. So, now we're just going to look at this GC1 function, and these are just going to go to 1 here, 1 here. So now we can rewrite this. So as the limit as S approaches 0, we have KC, K, we have 1 over S plus tau I, and we have our A, because we have to multiply by this A here, over our 1 plus K, KC, times 1 over S tau I. And then, so if this is approaching 0, so if S is approaching 0, that means this here is going to get bigger and bigger and bigger, right? Because it's getting closer to 0. And So that means the 1 over here is going to become negligible, so we can not account for that. And so then we'll have two functions that are getting extremely big at the same rate. So that will turn into 1. So it will be 1 times a. So a is our set point. So it shows that it will get to our actual set point. So that's the end of part 1. So part 2 says a system exhibiting inverse response to a transfer function of GP equals 2 over 10s plus 1 minus 1 over 2s plus 1. We're going to use the Hw4C analysis to determine the limits of stability for a proportion-only controller in response to the set point changes. Assume the measurement transfer function is 1. So we have here, let's say we have our set point coming in, and we have our process up here, process down here, right? So this is going to be your 2 over 10s plus 1, and this is going to be it's 1, 2s plus 1. 1, 2s plus 1. Okay. So we have these here, and then they're going to come together in this here. So this is going to be 3, this is going to be the first process here, this one here, this is going to be the second one here, right? So they come together, and then they split apart to the first and second process. So we can rewrite this as kind of our k1 over our tau 1 s plus 1, and then minus our k2 minus our tau 2 s plus 1. And so then we're going to do our common denominator and get them together. So it's going to be k1 times tau 2 s plus 1 minus k2 tau 1 s plus 1 all over our tau 1 s plus 1 times tau 2 s plus 1. And this is our, so now we want to put this in our GC1 function. So it's going to be KC multiplied by this function up here. So I'm going to copy and paste it. Right here, and then I'm going to divide this by 1 plus KC, and then it's at the bottom as well. So now we can look at our common denominators. So if we assume that we did this for this one here, then we multiplied it out to that 1, so we can actually cancel these, so that cancels out. So now we're going to look at this here. We're going to look at the polynomial in the bottom. So that is going to be, so let's expand that polynomial pretty much. So we have is our t1 s plus 1, t2 s plus 1, then we have our plus kc k1 t2 s plus 1, then minus k2 tau 1 s plus 1. And so we're going to multiply these out. So you get tau 1 times tau 2 s squared, and then you get plus tau 1 plus tau 2 times s, and then you get 1 plus 1 here, and then we have kc k1 tau 2s plus kc k1, and then you get k2 tau 1 s oh, this is also kc here, because you got to multiply this out here, so that's a kc. So going to be Kc, K2, 2, tau 1 S. Then you get minus Kc, K2. Okay, then what we're going to do is we're going to separate it from our, based off our S, so our squares, our 1, and then our zeros. So we have our first one is T1, T2, S squared, plus, and then we're going to have all of the ones that have S's in them, and we're going to bring them together. So tau 1 plus tau 2. And then we have our plus plus Kc, K1, tau 2, minus Kc, K2, tau 2, tau 1. Tau 1. And then this is S, and then we're going to have plus Kc, K1 minus K2, and then plus 1 is going to equal 0. So now we're going to use our Roth analysis to use this. So I'm going to copy this over to the next page. So we'll be using this. Copy. Okay. So with our Roth analysis, we have our tau 1 or tau 2. Then we have our Kc over Kc times 1 minus K2. And then we have our tau 1 plus our tau 2 plus Kc, K1, tau 2 minus Kc, K2, tau 1. And this is 0 over here, right? So we're going to cross multiply these two first, and then this one over here, and then we're going to divide by this here. So it's going to end up giving us Kc, K1 minus K2 plus 1. And so then this will have 0 over here. So if we do that again, where we cross multiply and then we divide by this function here, it's going to give us Kc. So with the Roth-Hertz analysis, you want all this stuff on the left side to be the same sign. So in this case, we want it to be positive. So if we find anything that could be negative, we need to find the parameters of it. So these two have these negative signs in there, so that could be negative. So let's look at that. So we have Kc, K1 minus K2 plus 1 is less than 0. So of Kc, and we'll have negative 1 over K1 minus K2. And then let's look at our other one. 1 plus K tau 2 plus Kc, K1 tau 2 minus Kc, K2 tau 1. So we want to solve for Kc. So if we move those over, we'll have Kc, and then we're going to pull out a Kc on this. So Kc, we'll have K1 tau 2 minus K2 K2 tau 1, and then this is negative tau 1 plus tau 2. So we have Kc is greater than is 1 plus tau 1 plus tau 2 over K1 tau 2 minus K2 tau 2. K1. Tau 1. Here. So now we're going to plug in what we got for what this was here. So yeah, so we have this 2, it's going to be our K1, this here is our tau 1, so this is equal to 2, this is equal to 10, 1 is K2 is equal to 1, and then tau 2 is equal to 2. Okay, so if we go back over, so we have Kc is equal to -1, and then our tau 1 is going to be, sorry, our K1 is going to be 2 minus 1. So this is equal to -1. So now let's look at our Kc down here. I'll just plug it in. So if we plug it in, we have negative, and then our tau 1, so tau 1 is 10, our tau 2 is 2, 10 plus 2, and then we have our K1, which is our K1 is 2, our tau 2 is 2, minus our K2, which is 1, times 10. Okay. So this gives us 12, -12 on top, and then we have 10, we have 4 minus 10 is 6. So we get -6, so that turns into a positive, and we'll have positive 2. So this shows us that our parameters for Kc are -1 to Kc to 2. So that is our answer.
I'm doing part C, 3. So we're going to use simulations to demonstrate the limits of stability that we determined in part C2. Okay, so we can go over to our Colab. I imported our libraries from GitHub. So the first thing that we want to do is we were given our GC is equal to 2 divided by n times s plus 1 minus 1 divided by 2 times s plus 1. And then we have our Kc as 1. And then we have our GC1 as we have Kc times our GC divided by 1 plus Kc times GC. Okay, and so now we can plug this into our formula. So we want to have our t and our y as what we're solving for. So we have our sim. We're going to be using our GC1 equation, our lambda as our time scale is going to be equal to 1. Our n is equal to our 1,000 steps. And then our dt, so the size of our steps is going to be 0.1. Okay. And now we have our fig that make subplots. So we're going to make our figures. And then so we're adding our scatter plot. So x is going to equal our t, our y is going to equal our y, and then our mode is going to equal our line. And then let's just update our layout. So the height is 100, width is 600. Let's see. Okay, so this is what it is showing. So we're having an inverse reaction to it, right? So we're having a low point and then a high point and then back to our set point, right? So what we're trying to find is to show that Kc can either be in between -1 and 2, and our Kc right now is 1, so it's going up and down and then it's hitting our set point and then being consistent, right? So if we change our Kc to, let's do -1.2, okay? So we can see that our set point is going down and it's not coming back up to what that what that regular set point was. So it's continually going down and continually getting less. So if we change it to something that's more, let's say positive, like 2.4, so in the opposite direction, right? So now we're having these squiggly lines, right? And it's getting bigger and bigger. And like you can see, this is 400, 600, and it's getting higher up here. So this is probably going to get even bigger. So again, it's not reaching a set point. It's getting more unstable. So past that -1 and 2, you have instability. So this proves that it's true for part C2.